This is the video podcast for Chapter 7 of Field Methods in Hydrology, addressing the topic of experimental design with sampling. Hopefully, you're not working too far ahead in the class, and you've now been on the first field trip, which was also associated for what's going to be homework number 2. And so you've had the experience of having to go out to a site without any preparation and be confronted with the problem of sampling. How am I going to characterize the bulk density of a plot without any other information or advanced knowledge of concepts or processes or whatever? So you had to work with your small group, figure out what to do, and go ahead with it. And so that should help motivate you now to think about how that could be done. How did you do relative to these ideas? So let's take a look and see what's involved. Of course, we cannot do a true census of all aspects of the environment at all possible locations down to the finest scale, at the continuum level, micron scale or whatever. We have more and more remote sensing technologies, and I'll be talking about that later in this presentation. But it's just inherent in science that we do sampling in both space and time. So what makes a good sampling scheme? And the image that I'm showing here is from a characterization of all the kinds of sampling that's been done in the ocean that could be used for a particular kind of study. And what you can see, something like the ocean is extremely difficult to sample because it's such a vast area with a lot of remote regions. And you can see there's a lot of random data, there's transects, just opportunistically getting information where you can. And how can we, as hydrologists, come up with rational schemes for sampling that are mindful of both the need to keep costs affordable while at the same time dealing with redundancy that's beneficial for hardware problems or just uncertainty. And of course, most importantly, as I addressed in the historical analysis and theory kind of behind field work, that preconceiving of what you expect to happen is essential in order to design how you're going to sample and monitor. I have a few concepts that I'd like to present up front before we get into the different alternatives of how to go about this. The first is, of course, that you have to know what it is you're trying to measure, what are those variables, and whether there's any inherent issues associated with making those kinds of measurements. But what this slide really emphasizes is that you do have to make choices about the trade-off of the accuracy and precision of what you're going to measure. No sensor can measure the widest possible range at the greatest possible detail or resolution. Usually, if you have to cover a wide range, then you have to accept less precision in what you're going to measure. And the topic of precision is important because today, when we analyze data using software like Excel or statistics packages or something, you can get return numbers that have 6 or 7 decimal places. Or, it will make a plot and it will just decide what number of decimal places or significant digits to use. But in fact, that isn't something that you should be allowing the software to decide for you. It's something you should be choosing mindfully. As with all other aspects of science, and the emphasis of this class, that making mindful decisions is important. And a key one is deciding at all stages, how precise do you think your information is? So precision reflects the ability to make repeated measurements and get the same number time and time again. The closer to the same number you get, the more precise it is. However, you don't have to have precision to be accurate. And so this bullseye plot on the right illustrates the idea. The upper right quadrant shows a target where if you were to make 4 shots, they're scattered around quite far apart from each other, but if you calculate the center of that, it's pretty accurate. I mean, it's not right in the center of the bullseye, but it's close to it. On the other hand, in the bottom left, you have 4 shots that are all very close together, so precisely repeating the same information, but they are systematically shifted off from the true location. So more and more we're becoming aware that accuracy can be obtained from having lots of samples of relatively low precision if you're willing to put in the time to get lots of samples. If you don't have a lot of time, then you don't want to repeat measurements, so then you want to spend more money to get accurate and precise estimates. Okay, so when we look at sampling, we have to worry about how you sample in space and time, and they're fairly similar issues. You can do random sampling in space or time. You can do uniform sampling. Okay, those are the most common of what you do. In space, since space is 3-dimensional or often just 2-dimensional, as we consider we don't worry about elevation usually, sampling through altitude. Then you could also have transects or clustered sampling. And then the last is the idea of looking at the domain you're going to sample and seeing if there's any governing structure to it. If there is, dividing it up into independent units, which we call stratifying that domain. And then internally, you could then sample, as shown here, with a uniform grid, but it also could be random or transect based within each strata. A lot of times random is thought as being an excellent way to go because it does remove a lot of potential for bias, and it is assumed in a lot of statistical tests that people like to perform. However, as I'll show you in a few moments, random sampling can be highly deficient in that it can leave large areas unsampled and unknown and have excessive redundancy in other areas. So random sampling is great if the domain is a random domain, if it has no inherent structure. If the domain is structured, then making a mindful sampling approach that cuts across that is really important. So that leads to the first fundamental question. Is the landscape a continuum, or is it an aggregate of units? Of course, the landscape is very rarely purely random. However, within subset areas, it may be effectively homogeneous, and therefore any variation within it is random. But most people think of the landscape as either a continuum or an aggregate of units. So a continuum just means that whatever domain you want to measure in, you can't really distinguish things. You can't classify it or break it apart. That it's just gently transitioning from one kind of land element to another. And if that's the case, then how you sample would be you want to orient relative to the continuum, cutting across it in different directions. Maybe random sampling would be adequate, but uniform sampling will probably work best. And then looking at how things change in space through different methods. The straight spatial analysis would be called covariance analysis. And then there's something called the frequency domain, which is if you think things are repeating, then you can take the data and think of it almost like a music or any other kind of signal. Then you can analyze it for its frequencies. Now, just because I put these weird names on the slide, I don't expect you to know. This may be the first time you've ever heard of these. If that's the case, what I'm trying to do is key you into where you could go for more information or more courses or methods you might come across, but how they fit in with field data collection is the key point I'm trying to make. Meanwhile, you could also have a building block perspective, like if the landscape is well delineated into patches of different vegetation type or soils or land use or topographic landforms, then you might want to sample internal to each one of those to characterize how it is, its conditions are, what are its hydrological, water balance or whatever. And here are just some examples of different kinds of ways that we tend to break up the landscape. So if you have a landscape as a whole, and here I'm illustrating with a stream network in a watershed context, if you want to say across a whole watershed, what is the mean value of something, or the total abundance of something, or what's the overall variability, then it could be adequate to come up with an overall statistical sampling scheme that just places samples randomly or uniformly across that whole domain without worrying about the building block, what are the strata that it's composed of. So the advantages of a straight statistical sampling is that you're spanning the system. You're not going into too much detail in a few places and extrapolating, like you're really spanning everything. You can use all the statistics associated with experimental design. You're going to get out of it very simple metrics like a mean value and a variance, or the shape of a probability distribution. And it's very well established for what works and what doesn't work and how to do this. Some of the disadvantages, though, is that this places more of an emphasis on characterizing what's quite abundant. If you're interested in things that are rare or transitions and edges, then this tends to not be useful. Also, processes that evolve over space, or especially space, may not be represented by individual points or transects distributed along this continuum. So those processes could be missed. And there could be far greater variability present than the number of samples that one can do. And so when you start with very simple ideas about sampling, then that leads to overly simplistic understanding of the environmental processes. And so that then in turn leads to poor choice of mathematics, and everything sort of flows from that problem. So there are just trade-offs to be made, and it just depends on what you're trying to answer. Let me show you an example of stratified sampling, because I think stratified sampling is a very common and important approach because, in fact, the land is divided up into different domains. I mean, whether you think of precipitation and orographic effects, or river morphology, or as shown here, the terrain associated with a large plateau region subjected to snow. So here's a study published in the journal Hydrologic Processes, and it shows a study area that's barren or partially covered with tundra vegetation. And so as a result, the distribution of snow based on catch and drift is governed strongly by the terrain. So 8 major terrain types were recognized, and it lists those. And it shows a map here in the upper left based on the aerial imagery that they have. They interpreted that to come up with this classification. And then from this, they came up with an approach for using snowmobiles to go out and sample and adequately represent what's happening in each one, which then led to maps of snow depth, density, and snow water equivalents that are mindful of these sharp thresholds between terrain types. Another important issue that comes up is the problem of how many samples to get within each strata. If you ignore strata and you just go out and say, okay, I'm going to get 30 samples across my area. If you sample using either a random scheme or a uniform scheme, the undeniable fact is that the samples will be proportionally weighted to the areas that are most represented in your domain. So for example, on the left, I have a number of landforms, or also we call morphological units, or channel units, or just MUs. And these are typical ones you've probably heard of for streams. And you can see, in this case, the abundance of each one along about a 37-kilometer section of a river. You can see that lateral bar is most abundant, and on the other end, chute is hardly abundant at all. Well, if I were to randomly sample 100 locations out of this whole river, by random chance, I should generally get a sample distribution that will reflect the area availability of these different units. So if I end up with 15 samples of lateral bar conditions and only 3 samples of chute, my relative ability to say anything about chute compared to lateral bar is different, because 15 samples is enough to make meaningful statistical analysis of lateral bar, while 3 samples of chute is totally inadequate. The solution to this problem is to replace proportional sampling that's mindless of the land to stratified sampling with equal effort. Equal effort means that we collect the same number of samples using the same method and the same field effort between each sites. So if we decide that we need 10 samples to ascertain what we want to know about a landform, then we should get 10 samples from each of these. And if that means that there's a lot of sampling in a relatively small area of chute, and remember, this is still 37 kilometers of river, so it's still not an inconsequential area. But then so be it. We have those 10 samples. We don't need to dramatically oversample lateral bar, swale, pool, slack water, just so that we can get an adequate representation of chute. If we mindfully stratify with equal effort, we can solve the problem. Another way of doing stratified sampling with equal effort is to start at the scale of a whole river and do some amount of sampling there, and then zoom in from there, like identify from the catchment scale analysis key areas of study, which then brings you down to what we call the segment scale, which is a length of channel equal to 1,000 to 10,000 times the average channel width of the river. Again, then get your number of samples, characterize the system, find the areas for prioritization, and go down, and then go down, and go down. So repeatedly honing in on the kinds of land that are of most concern. And this is particularly done in trying to prioritize limited dollars for management or restoration, problem solving in a watershed to get to the areas at the small scale that are most in need of help or in best position to be protected. Okay, so if we start with the idea that the land is not randomly distributed, but a lot of things that happen in hydrology are governed by spatially coherent landforms or patterns, then we need a way to represent that. And this is a little bit of a complex idea, so take some time to think this through. In the left, I'm showing a signal of random noise. Okay? It's very rare in the landscape or in hydrology that data is totally random. I mean, even if you look at precipitation data, it just doesn't look like that. Now, I guess maybe soil characterization within a very small plot might have some random elements, but it's pretty typical to see some kind of structure to what's there within the area you want to study. One way to represent that is to say, if I start at a point, as I move away from that point, how quickly does the pattern change? Okay, like let's say I'm standing in an area and that area is grass. If I move 10 miles away and it's still grass, that is highly correlated. But if I move 10 feet away and I'm not grass, now I'm swamp, okay, or I'm a forest, then it's totally different. So this is the idea of a spatial correlation structure. Remember, correlation is a measure of how similar two things are, or for the variable that you're choosing, how predictive one is of the other. They may not be one-to-one the same, but they're at least predictive of the other. And so what a correlation structure shows is just centered on any arbitrary point within your domain. If I move a little bit away from it, how similar or different am I? Different is indicated by having a low r-squared value. So this circular correlation structure is telling us that as I move away, no matter what direction I move in, I'm getting a little bit more different as I go away. Like maybe where I am, I have a certain color or a certain bulk density or a certain water content, and as I move away, it just decreases or changes from there. And the important thing is, and this is really the hard part where I think students get stuck, this is not a spatial map of your terrain or of your pattern. This is saying for any point anywhere in the terrain, you could center this on that, and this is how things change away from that point, regardless of of where you are. A different pattern is shown in the lower right where we have a correlation structure, but now it has a little bit of an orientation where from the lower left to the upper right, there is a higher correlation. And this could be like if a rainstorm is moving across the land, always in the same pattern, like southwest to northeast, then you might have a higher moisture content in a line that's oriented in that direction. But maybe as you move further to the north or the south, you would have of greater variability than you do along the line that something is happening. Another important issue that relates to this is how quickly does the change take place? So again, turning back to my grass issue, in the upper left here is an area that's all grass, or maybe it's an area that's all wet, all equally wet, or the same rainfall rate. So that would be homogeneous. There's no structure there. The middle scenario is a case where we do see a decrease, but the decrease is very, very gradual. Okay, and then the lower right is one where the changes are really abrupt. So from every 10 meters you get a more significant change or something like that. The idea of this is called the efolding distance. It relates to how close together or far apart the contours are. The closer together the contours are in this structure, then the more different the landscape or the pattern you're looking at is changing. So overall, these are fairly complex ideas, but they're essential because if you want to go out and measure something, what you measure needs to be mindful of these patterns. If there's no pattern to the land, then just go measure anywhere, right? It's just random. It's like a roll of the dice. And when you roll dice, you're just playing stochastic games, and it doesn't really matter what you do, where you do it. But in hydrology, the world is not usually random. Many things that we observe have patterns, and we need to sample mindful of that. Of course, now you're going to say, well, how do I know what the pattern is up front? Well, you can't always. Of course, experience can help guide you, and one of the goals of this course is to look at each variable and be mindful of what are the drivers that control pattern. So far, for example, we talked about precipitation, and the reason why I covered the ideas underlying precipitation was to put you into the idea like, hey, if I've got an orographic effect, I've got to sample relative to the pattern of that orographic effect, which might be something like this lower right spatial correlation structure. Okay, so then let's say you know something about that spatial correlation structure. How do we decide which sampling scheme is going to be best? So we have these four schemes to compare: random, a transect or linear type of network, clustered sampling, and a uniform network. Notice that we don't have stratified sampling because with stratified sampling, you can use any of these schemes after you have defined your strata. If you have a random array of data, of course, it's not going to matter because everything is equally valid. It just comes down to the number of points. But what happens if you have a centered, uniformly degrading spatial correlation structure or one that has an organized asymmetry to it? To answer that question, we're going to use a variable called the variance factor, and we're going to look at that as a function of the efolding distance. It's not that important to show you the math underlying the variance factor. If you really want to learn, I've given you the citation to the Morrissey et al. Paper in the journal Water Resources Research in 1995. What you need to understand conceptually is that the variance factor accounts for four things: the proximity of the gauges to each other, how well the gauges are centered on the correlation structure, the number of samples that you have and the overall size of the system, and then the amount of spatial variability that you have in the real data. What you can see here is if we start with the round correlation structure, let's just look at one example. So the thing with the open circles, which shows the highest variance factor, and high variance factor is bad. is the clustered example. So the clustered, that's just here where we have a dense network of points or observations within an, that's missing a lot of area unsampled. Of course, for a very low efolding distance where everything is highly correlated, again, as you tend towards homogeneous, it doesn't matter what sampling method you use. So they all converge on a very similar variance factor if the efolding distance is very small. But as that grows, we get a very strong differentiation where the clustered approach is far worse than anything else. Then the next is linear sampling, because again, these are the two that are missing the most amount of area. And then the interesting thing is that random performs worse than uniform. And the reason why uniform is performing best is because it is optimizing that the gauges are far away from each other and covering the totality of the correlation structure, and it's just centered all around the correlation structure. If we look at the oval correlation structure, in this case, uniform remains best, but now a linear design that cuts across the structure is going to outperform, random sampling is still better, but the linear structure that cuts across is the X's here, and the linear structure that goes with it is the circles, which is up here. So being able to cut across means you're sampling lots of different things, and what you can see is you're getting a pretty good result with that approach, but still uniform sampling is best. So what I get out of all this is, from the perspective as a hydrologist working in a world that is not random but is well structured, I like to sample uniform or stratified uniform so that I can get the most coverage and get the most, as it would say, the least amount of redundancy for the dollars I'm putting in. I just want to add, though, that this does ignore that there are benefits to redundancy. For example, if your tipping bucket gauges are going to fail, then you're missing out on information, and having some redundancy might help. Okay, so we're going to move on. That was fairly complex. Now let's think about how often you would measure in time. When you measure in time, we could take something like is shown here is the suspended sediment concentration based on a turbidity sensor. And here we can see the concentration in milligrams per liter. If I sample every 5 minutes, I get values anywhere from like 50 to almost 300 milligrams per liter. And there's a lot of fluctuation that's taking place in there, both very fast 5-minute scale fluctuation, as well as fluctuations and trends over days to a couple months. On the other hand, if I take monthly sampling data, so one sample taken once a month over a few years, I don't see all of that noise, but I actually have a fairly similar range. I don't get quite as low, and I get a lot, actually somewhat higher with one or two samples. But what I see out of this is 5-minute sampling, probably more than you need. Monthly sampling, definitely less than you need. So how do you decide how often you need? And this relates a lot to the same kind of questions you could ask. We could work on a temporal correlation structure. And when we talk about temporal correlation structure, we do have a term for that. It's called autocorrelation. Autocorrelation is a measure of how much a variable is different from one moment in time to another moment in time. So if I'm in the middle of a river, okay, and the flow is constant, like it's released from a dam, I could sample every 5 seconds, but the value is going to be the same, and it might remain the same over a month. But if I'm in the middle of a flash flood, then it might be changing very, very quickly. So the example of a dam release that's constant would be a very high autocorrelation, and an example of the flash flood would be a very low autocorrelation. How you go about doing autocorrelation, it's not very hard if you've already done just a generic correlation analysis. I don't think I have you do it specifically, but if you want to learn more, I would encourage you to just pause here if it's confusing and look up on the internet and just read up a little bit on some of the fundamentals of that idea. Okay, but what we did here is we took the data from the 5-minute sampling and we said, well, what if we just compare the value at any one moment with the value, say, an hour later or a day later, and then we saw what would happen. And what we found is that of course, the sample with itself is perfectly correlated, and as you shift a little bit longer, the R squared goes down and down and down, and it reaches a commonly used cutoff of 0.2 at a time of 10.3 days. It reaches 0 more around 18 days, but usually we don't worry about going to 0 because you've lost statistical significance usually long before that. So what this proposes is instead of sampling once a month or once every 5 minutes, the way to get the most bang for your buck is to go out and sample once every 10 days. If you do that, then any more sampling yields redundancy, and any less means that you're missing out meaningful changes in information. So this leads to then a desire to come up with a question: how many samples do I need in order to characterize something? And usually when we want to characterize something, it means that we want to obtain its mean value. And we'd also like to even go a step further and be able to articulate how accurate that value is. And there is a method in statistics for doing that, and this is something that I think it's beneficial for you to learn, and I'm going to ask you to apply this on your homework for homework number 2 to your bulk density data. So N is the number of samples you need. T is a number from a T table for a chosen level of precision, which could be like knowing the 95%, knowing to within a 95% confidence, for example. It depends on something known as the degrees of freedom, which equals N minus 1. S squared is a measure of the variance. Like we use S for like standard deviation, so S squared is the variance. We don't know the variance of the population of whatever it is you're trying to measure, of course, but we can get it from sampling. So either sampling or just rational thinking, you could say, well, what is the range of the parameter that's likely to be encountered at your field site? And R divided by 4 squared is taken as a guesstimate of what that variance is likely to be. Alternately, you can go out and collect, say 10 preliminary samples, use that to calculate S squared, like the variance of those 10 samples, and put it in here to see, do you need 100 samples or 20 samples or whatever. And then D is the variability in the mean value you're willing to accept. So I want to know the mean value to within what? To within 1 millimeter or 1 cubic meter per second or a billionth of a cubic meter per second. I mean, obviously, the tighter that you want it to be, the more precision you want, the more samples you're going to need. Here's an example calculation, and then like I said, I want you to do this with your bulk density data. So let's say I want to know the mean grain size of all samples collected on a sand deposit with a confidence of 95%. And I want to be within 0.01 millimeters of the actual mean of that population. That's a very tight standard, I would say. Although, for grain size, we usually can work down in the micron level, and this is in the tens of microns. So from field samples taken in a preliminary survey, we found that this variance is 0.1 millimeters. So from that, I can then estimate my variance. And now here's the tricky part. In order to do this calculation, the problem is that T is a function of degrees of freedom, and degrees of freedom equals N minus 1. Well, now we have a circularity because I can't break down N minus, the function of T with N in 2 places in a nonlinear way. So what you do is you start with just a raw guess, like just make it up. So I'm going to just start with a raw guess of 10. I need 10 samples. I could have guessed 100, 1,000, or whatever, but I'll start with 10 because that's a nice small number I'd like to collect. So I take 10, I subtract 1, and I get 9 degrees of freedom. I go to a t-table, and this is one I pulled off of Wikipedia, but there are better ones on the internet, so you can see what you can find. And notice this only goes up to 25 samples, so if your answer is going to be more than 25, you need to find a better table. I'm going to go to the one-sided t-table to the 95%. Why am I going to the one-sided? That's a statistics question, and if you want to understand that, there's a really good short 5-minute video on the Khan Academy about the choice of one-sided or two-sided in statistical testing. So I encourage you to go take 5 minutes and look that up. When I do that, I go down to 9 samples there, and I get this value of 1.833. I put that into my formula, and I calculate 21 samples. Well, I started with a guess of 10, I ended up with 21. So that's quite different. That means that I should not be satisfied, and I should take 21, which is now a better guess. I'm going to put that into the function again, get my degrees of freedom of 20, get a number of 1.725, put that in here, and now I get a number of 19 samples. So see, I've gone from 10 to 21, which was a big jump, to 19, which is just a small little modification. If I put 19 in, I get 18 degrees of freedom, I get my t-value, compute again, and I get n equals 19. So finally, the number has stabilized, it's not going to change anymore, and we call that convergence of that number. So this means that in order to know the mean grain size of the samples with a confidence of 95%, and to be within 0.01 millimeters, I have to collect 19 samples. See, that's a pretty useful, practical skill I've just given you that you can use in your professional career. Okay, so one last just nuance will come up again later in the quarter, but of course when you're designing an experimental study, making a decision about how you're going to make a measurement in terms of sensors or sampling or whatever that's going to be, you have to consider all these kinds of issues that we're talking about in the class. And then you also may need a data logger, and that's going to be important too. So this is just more of like a nod to things we're going to be looking at throughout the whole quarter, and with regard to a future presentation on data loggers. Now I'd like to throw in a caveat, because personally I have to say I'm not particularly satisfied with the scientific paradigm of sampling. Yes, it's the dominant paradigm and we all have to do it to some degree. But things are changing very fast right now in the 21st century. We're actually getting away from sampling and going more towards a more complete characterization of the population, primarily through the use of remote sensing methods. So some of the reasons why we should be unhappy with sampling, I've already covered a little bit. But most importantly, missing the complexity of spatial patterns to me is the fatal flaw. Because so much of what we have in hydrology, geoscience, environmental science, it's all about the spatial complexity of nature. And if we can't sample that in enough detail, then we just cannot understand or replicate those phenomenon and be good stewards of the land. And everything then cascades from there, because we start with an oversimplified understanding of the land, which then results in oversimplified assumptions and equations, and everything just sorts of falls apart. And the worst part of all is that we get so convinced by the elegance of our science based on sampling that we get an excessive high confidence that we know the right answer. We do not respect our own inadequacies in our scientific understanding. And then that leads us to then go out and take actions in the environment, which instead of helping the environment actually degrades it further. And so that just leads to this quote that I've pulled totally out of context, but it just says that we never can rest. We can never be satisfied with what we know. We have to keep pushing on. And that's just more evident today than ever, because we always see that whenever a company, or I've seen certainly plenty of scientists who decide to stop innovating and just keep doing what they do with no further change. If you don't change, you're going to become irrelevant. You're going to become outdated. And just one example of this, and there's so many of them now in technology, but one of the first big examples was the Atari video console system. As soon as it was built, the founder of the Atari said, okay, it's time to move on. What's next? But instead, the company that bought Atari said, no, we're going to mine this thing. We're going to get as much profit as we can out of it. And what they did is they basically just ran it into the ground. And that's what we often see in science. And so while we can appreciate the value of sampling, and I've tried to cover that, we have to think of what's next. And in my view, what's next is what I call near census studies, which could be, in this case, near census environmental science or hydrology or river science or whatever. Why did the term near census? Well, a census means you're getting everything, like the complete population. And when it comes to nature, you can't sample everything. So I like the idea of a near census, of like trying to get near to that. So it means comprehensive, spatially explicit, process-based studies using the 1 meter scale as the basic building block for investigating landscapes. 1 meter is pretty darn detailed. It's not detailed enough for some things, but it's pretty darn good. If we could characterize the land in 1 meter resolution and capture the essential physical processes and ecological functions at that scale, boy, we would be pretty well off. So how do we do this? Well, you have to collect geospatial data, and I've already given you a presentation using LiDAR and multi-beam to collect this kind of data for topography. You have to then have some kind of meter scale mechanistic predictive model, and that's far beyond this class, but it could be a groundwater model, it could be hydrological, hydraulic, morphodynamic, whatever kind of model. Then you have to layer on top of that model whatever kind of empirical functions you need to extrapolate beyond the state variables of the model to the environmental variables of interest. Take those outputs, stratify the results that you have from 1 meter resolution into whatever the basic building blocks or spatial scales that are relevant. And then synthesize that. Here I have for river assessment, but it could be for anything in the environment. And the most important thing about this near census approach is it also then gives you the ability to change that data and see how the system would work with different project alternatives, so like in a restoration of the land kind of mode. So here's just some examples of near census data. Low aerial imagery is becoming very popular. In the upper right is a standard 1 meter resolution image that you might see from a traditional vendor. That was considered very, very good. And I've overlaid that a image from low aerial imagery, and of course you can't see it full resolution. So then if I zoom in even further, you can see individual grains down to the 10 centimeter size. We have 4 centimeter resolution in this photo. LiDAR I've already talked about, but just as a different example, here's a map of a section of river where we've classified the canopy into 3 different height classes, which tend to represent different kinds of vegetation, like small shrubs, resilient woody shrubs, and then trees, riparian trees. Of course, topographic maps is the easiest to generate using a combination of techniques for through water and exposed terrain. So overall, sampling is a dominant paradigm. When you sample, you have to be mindful of the underlying processes and associated spatial and temporal patterns and dynamics. That's really the key message I'm saying throughout this whole course. I'm trying to give you an opportunity to get experience with typical metrics that you're going to have. What are the analyses you do, and what are the kinds of conclusions that you can make out of those standard approaches from sampling? However, into the future, sampling is going to give way to more and more near census kinds of methods, so you should also be thinking about where that might take you. Okay, so that's the presentation, and we will move on to Chapter 8 next.